Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks, section 12.1. We're getting into the probability chapter, which will still kind of just be an extension of counting. Right, chapter 10, chapter 11, we're on counting methods, counting principles. 12.1 is called the probability of an event. What is the likelihood of some event occurring in some experiment? And like I said, you're going to see that it's just going to be a lot more counting. But after we count some things, then we're going to divide them. Right? So not too much more to do in this chapter. So here, one of the primary applications of counting is to calculate probabilities of random events. Probability theory plays an important role in almost every area of science, economics, and business. In computer science, randomization and probability are ubiquitous, right? Widespread, used a lot. Right? Here are a few examples. Well, you can read these examples, because what you're going to see here is that a comprehensive introduction to probability theory and its role in computer science is beyond the scope of this material. So we're not covering it. Instead, the focus here is on how counting is used in probability. Right, so to kind of tie it back to the previous couple chapters. So consider a simple example in which a red and a blue die are thrown. A player in a game of dice may be interested in different types of events that can occur as a result of this throw. For example, she may be interested in the likelihood that both dice come up with an even number, or that the sum of the numbers on the dice is at least 8. The simple example of throwing a pair of dice contains many of the basic ingredients studied in probability. Alright, so we get into a new chapter, so getting into some definitions here. Experiments and outcomes. An experiment is a procedure that results in one out of a number of possible outcomes. So the results of a procedure are called outcomes. The set of all possible outcomes is called the sample space of the experiment. A subset of the sample space is called an event. All right. So they go through some examples here. So in the case of the red and blue die that was described up here, the experiment is the process of throwing the dice. An outcome of a roll of the two dice is the number that shows up on the blue die and the number that shows up on the red die. The picture below shows two different outcomes of a roll of the dice. Right? So one outcome is 5 on the blue, 3 on the red. Another possible outcome, 3 on the blue, 5 on the red. And these are different outcomes because the same numbers are showing up, 3 and 5, but they're showing up on the different dice. So that's why they're different outcomes. So for simplicity, we describe an outcome by an ordered pair. Right? So you don't have to keep drawing all these pictures. Where the first number denotes the outcome of the blue die, and the second number denotes the outcome of the red die. The outcome on the left, this left picture, is 5, 3. This is 3, 5. The set of outcomes then for each die is 1 through 6, and the sample space, right? The sample space, which would be the list of all possible outcomes, is the Cartesian product of the outcomes for each die, right? Because remember, a Cartesian product of two sets would form all these ordered pairs, right? So you'd have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 3, 1, and so on, all the way up to 6, 6. and that's called the sample space, the set of all possible outcomes. An event is a subset of the sample space, which again, the sample space is usually denoted by S for sample space. For example, the event E, that the sum of the dice is exactly 8, is the following set, with the ordered pairs 2, 6, 3, 5, 4, 4, 5, 3, 6, 2. Right? These are all the outcomes that have a sum, the sum of the two dice is exactly 8. And this is a subset of S, right? This is a sub-collection of all the ordered pairs that belong to the sample space, right? The list of all possible outcomes. So just some examples to read through, hopefully giving you an idea as to what these definitions mean, how they're used. So some other examples. All right. Standard playing cards. Another common example of an experiment is a card dealer who deals a hand with 5 cards to a player from a perfectly shuffled deck. A standard deck of playing cards, in case you didn't know, consists of 52 cards. Each card has a rank and a suit, right? Like a number and a suit. There are 13 possible ranks, right? Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. And 4 possible suits, right? Diamonds, hearts, clubs, spades. Any rank suit combination is possible, resulting in 13 times 4, which is 52 different cards. The different ranks and suits I already read out loud. I already said them out loud. Those are the ranks, those are the suits. So the 8 of hearts, for example, will be denoted here just with 8 and then a heart next to it. Right? The sample space of 5 card hands consists of the set of all 5 subsets of the 52 cards. So, right, the order in which the cards are dealt is not important, right, as long as you just have them in your hand. Just the set of cards in the hand after the cards have been dealt. For example, one possible outcome of the experiment is this here. And again, notice they put the braces instead of parentheses because the order doesn't matter. So here's one possible outcome with one hand, 2 of hearts, 2 of diamonds, 8 of spades, Jack of clubs, Ace of clubs. The number of different outcomes from dealing a 5-card hand, as they mentioned already, was the number of 5 subsets of the 52 cards, or 52 choose 5. Now, so that means the sample space, right, the list of all possible outcomes, has this many elements in it, right? There are this many 5-card hands that can possibly be dealt from a 52-card deck. And then you have here an event that is a subset of the sample space. The event E Jack, right? E sub Jack. The event E Jack, that the hand has 4 jacks, would be the set of all hands of this form, where you have all 4 jacks in the subset and then some other card. Right. So the number of outcomes of this set is 48. Right, the number of outcomes in this event is 48. So now we talk about finding, okay, well, then what would be the probability? All right, what would be the probability of being dealt a 5-card hand and getting all 4 jacks in your hand? Well, we're going to see it's just the number of ways that can happen, 48, divided by the total number of possible outcomes, the size of the sample space. So it'd be 48 divided by, whatever 52 choose 5 is, some huge number. So, that would be a very tiny number, right? 48 divided by something huge. So the probability of getting dealt a 5-card hand with all 4 jacks is very, very small. So they talk about probability here. Now they talk about the difference between discrete and continuous probability. Discrete probability is concerned with experiments in which the sample space is a finite or countably infinite set. Countably infinite means that there is a one-to-one correspondence between the elements of the set and the, well, they say the integers. You could also say just the positive whole numbers, the counting numbers, 1, 2, 3, 4, 5, etc. An infinite set that is not countably infinite is said to be uncountably infinite. So again, now we're not going to get into all this. I'll just give you some examples right now of countably infinite sets are, the positive whole numbers, 1, 2, 3, 4, 5, the counting numbers. The integers are countably infinite. You can form a bijection between the counting numbers and the integers. The rational numbers are countably infinite. All right, and then for uncountably infinite, we're talking like the real numbers, or any interval of real numbers on the number line. The complex numbers, right? Those are uncountably infinite. You can't form a bijection between the real numbers and the counting numbers, for example. Anyway, that's beyond us right now. So they give you examples of countably infinite sets. The set of all binary strings of any length is countably infinite. The set of ordered pairs of integers is countably infinite. The set of rational numbers, as I mentioned, is countably infinite. The set of real numbers is uncountably infinite. In fact, the set of real numbers in any interval, right? Just the real numbers from 0 to 1 is uncountably infinite. And here is an example of an experiment whose outcome is not countably infinite. Say a dart is thrown at a 1 meter square target. The point at which the dart lands on the target is an outcome of the experiment. The sample space of all possible outcomes is best modeled by the pairs x, y in the range from 0 to 1. There's an uncountably infinite number of possibilities there where the dart could land. Now we're mostly going to be dealing with discrete probability, where our sample space has a finite number of elements, like 52 choose 5 from the 5-card hand thing earlier, or a countably infinite set, like just the counting numbers or just the integers. All right. So in activity related to some of these words up here, right? So in the experiment of a 5-card hand, right, dealing a 5-card hand from a 52-card deck, is the following an outcome or an event? This is an outcome. This is just one possible 5-card hand that you could get. So this is an outcome. Is the following. Now again, pay attention to your braces. If there was a second set of braces around this, it would have been an event, because it would have been the set with one hand in it, one outcome. But it has just a one set of braces, so it's just a single outcome, a single 5-card hand. Now this one has the second set of braces out here. So this is the set with 2 5-card hands in it. So this is a subset of, all possible 5-card hands. This is an event. In that example of the red die and blue die that are thrown, define the event E to be the number on, to be that the number on both dice are multiples of 3. So which set corresponds to E? Well, 3, 3, 3, 6, 6, 3, 6, 6. This set here, this set of those outcomes would be event E, the way they described it. So suppose a coin is flipped 3 times. The outcome of the experiment is the sequence of outcomes from each flip. For example, HHH denotes 3 heads on each flip. How many outcomes are there? Well, you could also think of this as strings formed with H's and T's, say heads and tails. So how many strings of length 3 can you form with H and T? That'd be 2 times 2 times 2, 2 to the third, that'd be 8. in that experiment was where the coin is flipped 3 times, which set corresponds to the event that at least 2 of the 3 flips come up heads? Well, this one. Every single outcome in here has at least 2 of the 3 outcomes are heads. Right. So again, hopefully you understand experiment, which is some procedure you're performing. An outcome is just a result of that procedure. One result. The list of all, the set of all possible outcomes is the sample space, and then any subset of that sample space is an event. All right, so here, a natural question to ask about an experiment is, what is the likelihood or probability that a particular outcome occurs? So before we get into answering that question, they have a new definition for us. A probability distribution over the outcomes of an experiment with a countable sample space S is a function p from S to the set of real numbers in the interval from 0 to 1, meaning that every outcome has a probability between from 0 to 1. And you may have heard this before, right? The probability that an event occurs can be anything from 0 to 1. If the probability of an event is 0, that means that that event can't happen. And if the probability of an event is 1, that means that event is guaranteed to happen. And then every other probability is something between 0 and 1. Again, and you can change that to a percentage if you want. If I say the probability of an event occurring is a half, that means there's a 50% chance, right? A half, 50% chance that that event will occur. And if you look at every single outcome in the sample space, right? See, this is the sum over all S belonging to S here. So if you look at every single outcome in the sample space, all possible outcomes, and add up the probability of every single outcome, it should add up to 1, right? Because everything in the sample space, at least one of those things is guaranteed to occur. So the sum of all those probabilities should be 1. The probability of outcome S is denoted P of S, right, like this function they mentioned. Now, if E is a subset of S, right, is some event E, the probability of event E is just the sum of the probabilities of all the outcomes in E, right? So for all the outcomes of E, you just add up the probabilities. So, for example, consider a dishonest dice player who shows up to a game with a loaded die. The player's die is biased so that an outcome of 6 is twice as likely to occur as the other numbers. So define an experiment which is the roll of a single die. The sample space is, you can get an outcome of, you can roll a 1, a 2, a 3, a 4, a 5, or a 6. And the probability distribution, right? Again, the probability distribution is simply you list off the probability that each event in the sample space occurs. Right? The probability distribution over those outcomes is defined this way. So again, they said that the probability that you roll a 6 is twice as much as the others. And all of them have to add up to 1. Right? That's what this said up here. So now again, the way you could figure this out, right, without stating that, they stated it for us, but the way you could figure out what the probabilities needed to be is say the probability of rolling a 1 is X. Say you don't know what it is. And this is the same as the probability of rolling a 2 up to the probability of rolling a 5. And then they told you that the probability of rolling a 6 is double the probability of rolling any other number. So say 2x. And the sum of all these probabilities must be 1, right? And this is for all the s's, for all the outcomes in the sample space. So we're getting 5x plus 2x, right? The x plus x 5 times. 5x plus 2x must be 1. 7x must be 1. X must be 1/7. So all these are 1/7, and this is 2/7. So that's how they got those. Okay. So now they talk about an event, a subset of the sample space. The event that the die comes up an even number, 2, 4, 6. What's the probability of this event? What's the probability that the die comes up even with this loaded die? So it's the probability of rolling a 2 plus the probability of rolling a 4 plus the probability of rolling a 6. You just add up the probabilities for each outcome in that event, which will be here 4/7. Right? So got over a 50% chance that the dice comes up even. Right? 4/7 is over 50%. Right? So in the loaded die in the example above, what is the probability of the event that the number on the die is 5 or 6? Well, probability of rolling a 5 is 1/7. Probability of rolling a 6 is 2/7. Add those up, you got 3/7. Simple as that. Right. Now they're getting into a specific kind of distribution. Right? They talk about a probability distribution here. Here's a specific kind of distribution called the uniform distribution. So in many scenarios, the probability of every outcome in the sample space is the same. Or they would say that every outcome in the sample space is equally likely. You may hear those words. The probability distribution in which every outcome has the same probability is called the uniform distribution. So since there are cardinality of S outcomes in the sample space S, and their probabilities must all add up to 1, under the uniform distribution, for every outcome in the sample space, then the probability of that outcome must be just 1 divided by the size of the sample space. Simple enough. The uniform distribution reduces questions about probabilities to questions about counting. Because for every, if you're talking about a uniform distribution, if every single outcome is equally likely, every outcome in the sample space has the same probability, then for any event, E, the probability of that event occurring is just how many elements are in that event divided by the number of elements in the sample space. So you're just doing some simple counting and then division. So returning to that experiment with the red die and the blue die, right? If the dice are fair, then each of the 36 possible outcomes is equally likely, right, with a probability of 1 out of 36. So then the event that the sum of two numbers is 8, right, which have these outcomes, is 1, 2, 3, 4, 5. 5 out of 36. The size of this set divided by the size of the sample space. And again, you can only do this, you can only apply this formula when every outcome in the sample space is equally likely, when you have this uniform distribution. All right, and then I'll let you read the example with the 3 flips of a coin here. All right. So here, give your answer as an integer or a fraction simplified to its lowest terms, right? So 3/4 instead of 9/12. So in an experiment consisting of 3 flips of a fair coin, what is the probability that the first 2 flips are both heads? All right, so I'll go to a paper. So here, the experiment, the procedure being followed here is, flip a fair coin 3 times. So here's S. Now you can get heads, 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 tails, heads, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads, tails, heads, tails, tails, and finally tails, tails, tails. Now I didn't need to do all that. All right. The size of S is clearly 8. Right? You had 2 times 2 times 2, 2 options, two outcomes for each, 2 possibilities for each. And the fact that it's a fair coin, means that every single one of these has the same probability. Right? Just like the fair dice example. So the probability of each one of these, so each outcome is 1/8. So this has a uniform distribution then. Right? Every single outcome has the same chance of occurring, about 12.5%. Now, the event they are describing is that the first 2 flips are heads. The first 2 flips are heads. So that's heads, heads, heads. The first 2 flips are heads. Heads, heads, tails. And that's it. All right, looking through these, those are the only two outcomes where the first 2 flips are heads. And the cardinality of this event is 2. Right? There are 2 outcomes. So the probability of this event, remember, in the uniform distribution scenario, only in this scenario where every outcome from the sample space is equally likely, is the size of that event divided by the size of the sample space, or the cardinality. So 2 out of 8, which reduces to 1/4. So if you were to flip a coin 3 times, you have a 25% chance of flipping 2 consecutive heads from the get-go. Right. So I'm entering 1/4 here. All right, so again, 3 flips of a fair coin. What is the probability that the first 2 flips are just the same? So now my event, I'll just put up a different piece of paper over this. So now my event, E, or you can call it whatever you want. Just using E for event. Where the first 2 flips are the same. So I mean, first 2 flips are the same there. First 2 flips are the same there. But also they could be tails. Right? Those are the tails, 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 heads. And that's it, right? Looking at all the possible outcomes in the sample space, there are only 4 outcomes here. And again, since we're in this uniform distribution scenario where every outcome of the sample space is equally likely, the probability of this event is 1/2, right? 4 out of 8. 4 out of 8. And this is the rolling the red and blue die. Remember, there were 36 possible outcomes that were equally likely. Again, if the die were fair, 36 equally likely outcomes, a uniform distribution. And I'll leave this one to you. All right, then you have a challenge activity where, again, you're asked here, 2 dice are rolled. Enter the size of the set that corresponds to the event that both dice are odd. And this is a 6-sided dice, right? You D&D players out there, I know that there are many other dice out there with more sides, like D20s and stuff, but we're assuming a 6-sided die here, 2 6-sided dice. So again, we're assuming they're fair. All right. And all they're asking is, how many outcomes have these odd dice? Well, for the first die, there are 3 options. So I'm just going to apply that principle of counting, the fundamental principle of counting. 3 options, 1, 3, or 5. And then multiply that by the 3 odd numbers on the second dice. 3 times 3. There'd be 9 outcomes where both dice are odd. Now they wrote it out for us, those 9 outcomes, but you didn't have to, right? You just have to count. You don't have to list. The second level. Again, enter the size of the sample space when 5 coins are flipped. So, or flipping a coin 5 times. That'd be 2 to the 5th, 32. 2 6-sided dice are rolled. Enter the probability that both dice come up with odd numbers. Well, that's 9 out of 36, which reduces to a quarter. I don't know why I said all these out loud, but pretty simple, I feel, to begin with. I'll let you read this example. I don't really feel like this. You can read through that. This is another interesting one where you talk about, going from one point on a grid to another point, but you can only make certain moves. And it corresponds to forming a word, forming a string with, so many letters. Say I can only go up and to the right. How many ways, how many possible paths are there from point A to point B if all I could do is move up and right? So you see how this string that was created in this move has what, 3, 6, 9, 11. It's a string of 11 letters with 4 U's and 7 R's. So that'd be 11 choose 4 or 11 choose 7. Just choose where the U's go, choose where the R's go, and that'll count how many different paths there are to get from A to B. And I'll let you read that more so as well and look at this animation. All right. Here they even talk about you have to go through X. So then you use the multiplication rule. Count the number of ways to get to X, and then multiply that by the number of ways to get from X to B, and then divide that by the total number of ways to get from A to B. And that'll give you the probability that you picked a path from A to B that ran through X. So again, I'll let you read that as well and watch the animation. Another example with 5-card hands. And if we're talking uniform, again, most of these examples will be for uniform distributions where every single possible outcome is equally likely. So I'll be ending up using this formula where you count the number of objects, the number of outcomes in the event, and then divide by the total number of possible outcomes or the size of the sample space. So again, I'll let you read this. It's all the same principle, and we're applying counting rules. Now, let you play this animation here, right? It's just, if you're dealt 5 cards, what's the probability of getting a 2-pair hand? They use counting principles to count the number of hands with 2 pair, divided by the total number of 5-card hands, and you get your probability, right? A little under 5% chance of getting a 2-pair. Lots of just counting principles. So if you didn't do well in chapter 10 and chapter 11, suggest going back and refreshing. Alright, so let me look at this activity here. So in the grid graph shown below, what's the probability that a random direct path from A to B goes through the vertex in the upper left corner? So a direct path from A to B. So again, you can't go backwards, meaning, right? You have to go right or up. You can't go down or left. You can't go away from B. You have to go towards B. Now I'll pull up a piece of paper here. I'll actually just have it come up on screen. Hopefully you can see this. Now if you look at this, from point A to point B, if I'm doing a direct path where I can't go back, I can't go down, right? I have to move toward B in some way on these grid points. Do you see how across there are, 1, 2, 3, let me count it with the mouse here. I'd have to go to the right. 1, 2, 3, 4, 5, 6, 7. I'd have to go right. 7 rights. 7 R's. Right, I'll call R right. So I'd have to go to the right 7 spaces, 7 points. And then how many ups are there? I'll call these U's. There are, from the bottom to the top, there's 1, 2, 3, 4. 4 U's, 4 ups. And I could take this path, right 7 up 4, and get from A to B. But no matter how I go, again, it has to be direct. I can't go left, I can't go down, I can't go away from B in any way. No matter how I go, even if I do a zigzaggy motion, at some point I have to move right 7 times and I have to move up 4 times. So the total, right? So the total number of direct paths, the total number of outcomes, the size of the sample space, whatever you want to call it, would just be 11, choose 7, or 11, choose 4. Because again, I have to make 11 moves, 7 rights and 4 ups. I just have to choose which order they come in, right? So I choose, if I have a slot for each of my 11 moves, I choose where the 7 R's go, or I choose where the 4 ups go, and then the R's have to be the rest of the way. So it's 11 choose 7 or 11 choose 4. Now, right, so yeah, this is the size of the sample space, right? The cardinality of S. Now the event, I'll call it E again. The event they're talking about here, they're saying, what is the probability that a random direct path from A to B goes through the vertex in the upper left corner? Right, so the very upper left corner vertex. So going up to here and then going to the right. Right. Well, if it has to go through that upper left corner, and it's a direct path, right, meaning no going away from B at any point. Can't go down, can't go left, have to go up or right. That's the only way I could do it. I'd go up, 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 hit the upper left-hand corner, and then I would have to go right 7 times. So there's only one path. Right? The size of this event is 1. There's only one outcome, one path that goes through the upper left-hand corner and is also a direct path that they're talking about. So the probability, if I were to choose a direct path from A to B at random, the probability that that path goes through the upper left-hand corner would be 1 divided by whatever 11 choose 7 is, or 11 choose 4. And that's this third option here, which you're going to see comes up, correct, and they explain and all that. So, how about this one? If a red and a blue die are thrown, again, let's assume they're fair dice, so we have the uniform distribution, right, the same probability for each outcome. Then what is the probability that the numbers on the 2 dice are the same? So, well, there's only 6 ways that can happen. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. So 6 out of the 36 total possible outcomes. Now 6 out of 36 is 1/6. And then here, what is the probability that a random 5-card hand from a 52-card deck has all 4 aces? All 4 aces. Well, the denominator is going to be 52 choose 5, which you're seeing here and here, right? You know, the total number of possible outcomes, the size of the sample space would be 52 choose 5. And the numerator would be the number of 5-card hands that have 4 aces. And this is exactly like the question with the 4 jacks hand earlier. You know, so if I gave someone here, you take, you have all 4 aces, and then some other card. And there are 48 other cards, so you'd have 48 choices. There are 48 different hands in which you could have 4 aces, so the numerator would be 48. And this is very much exactly the same as the one with the 4 jacks read to you earlier. All right, so again, a lot of I know I skimmed over some examples. I said you can look at them on your own, but really, it's just a lot of counting. You apply counting principles you've learned to count the number of outcomes in the sample space. Read the event they're talking about. Hopefully you understand the event, what they're saying, what they're looking for, so that way you can then count how many outcomes are in that event, and then divide those two numbers and you'll have your probability. And again, this is only good if we're talking about a uniform distribution, if every outcome in the sample space has the same probability or has an equally likely chance of occurring. And this is it. And this is all we're doing. We're not going beyond the scope of this. All right, for this section anyway. All right, then you have your additional exercises. I don't believe I didn't assign all of these, I don't think. But I would still recommend looking at all of them, right? Get more practice, more exposure, maybe get better at the material. You can also, look at the solutions if you need to. Right? Just as a check, though, just to see how you're doing. Please try to work them out first before you look at the solutions. And hopefully this video was a good guide for this section. And if you have any questions, of course, send me a message and I'll get back to you as soon as I possibly can. And thank you very much for watching.